Polynomial functions of higher degree. So yesterday we looked at just quadratic, in other words, just x squared. Today we're going to look at larger ones. Okay? Now, visually, from a graphing perspective, a polynomial will always be continuous. It won't have any sharp angles, and it will always be connected. Okay? So the idea is if you have a graph that looks like this, well, I can guarantee you that's not a polynomial because there's a big gap in it. It does include every single x value there, but that just makes it what type of function? Piecewise. That's a piecewise function. It's not a polynomial. Okay? Graphically, if we look at the default polynomials, where you have like x squared with nothing else added, x to the third, x to the fourth, x to the fifth, with just nothing tacked on, they behave a lot like the smallest versions of each. X to the fourth looks a lot like x squared. The only thing is it's flattened out at the bottom, and it's steeper on the edges. X to the third is that normal S-curve thing we think of as it goes through the origin. But when it's x to the fifth, x to the seventh, x to the ninth, all it does is get to the x-axis that much faster and then stay along it until it spikes up and away from it again. So it just kind of flattens out around wherever its vertex is. Okay? Now these are also sometimes called power functions, when all it is x to 1 power, when it's nothing else tacked onto it. You might have a coefficient on it, but they're not going to have like x to the fifth plus 3x to the fourth minus 8x to the third, that kind of stuff. Those are just basic power functions. So if I have a basic power function that looks like these, okay? Well, if I want to sketch this. Now, when they say sketch these, I want you to try to do them without the graphing calculator to start. Okay? Because if I just look at this, this is x to the fourth, right? What is the plus 5 in parentheses here going to do? Move it 5 to the left. So essentially what I have here is a vertex at -5. And then if I compare this to a regular y equals x squared, what's going to be the difference? Yeah, it's more straight on the edges and flat in the middle. So in other words, go along the x-axis a little bit before going up, and then go straight up. So something roughly like that for a rough sketch. Okay? What about this one? 3 units to the right. Then? Well, it's not quite 4 times because the problem is horizontally. Remember, that would go inside to affect it horizontally.
It's going to go up slower.
It's going to increase at a slower pace, something along those lines. Okay? So the idea is it's still going to be opening up. It's still going to have that general behavior. But it's going to be, it's going to take longer essentially to go up. So it's going to look roughly, well, not as much as you think, because the problem is it flattens it out. So it's going to look fairly similar. But yeah, if I could just compare, here, I'll graph both of them for you. If I just compare it without that, -3 raised to the fourth. So if I just graph both these with and without, there's with the 1/4 out front. 8.5 hours later, there's without. Doesn't affect it quite as much because that raise to the fourth makes it grow so quickly as soon as you're more than 1 away, that it doesn't actually smash it as much as what it would for just x squared. Okay? Okay. One of the other main things from this section is what's called the leading coefficient test. Now the nice thing is that when you have a power, okay, when I have something that's raised to the third, to the fourth, to the fifth, something like that, that alone gives me a rough idea of what it looks like. It either looks roughly like a parabola, just kind of changed a little bit, or roughly like that S-curve that the cubed gives you, right? So the idea is, based on what that biggest power is and what the leading coefficient on that term is, you can actually tell quite a bit about the graph. I can tell if this is raised to the third, that it's going to do something like this in the middle of it. If A is positive, I know it's going to start low and end high. This book will describe that as it falls to the left and rises to the right. Well, I'm lazy. I don't like to write that much. Okay. And plus, the way I learned it was I would just literally describe this as down and up, describing which way the arrows are pointing, essentially. If you want to write falls left, rises right, that's fine as well. Now, that one is different than when you're just looking at whether it increases or decreases, because that goes left to right. This goes kind of from the center out. You're describing what's going on at the ends of the graph. So if that one's down up, what would this one be when A is negative? Yeah, up, down, or rises to the left, falls to the right. Okay? Now, when I go to one that's an even power and make the leading coefficient positive, what's that one's end behavior going to be? So if it's x to the 4th, x to the 6th, x to the 8th, and the leading coefficient is positive. What? Yeah, up and up. And then if it's negative, down and down. So it look like that. Okay, now all that's telling you is what's going on at the ends. It's not telling you what's going on in the middle here, just what's going on at the ends. But often that helps you also get a more accurate, rough sketch of these things. So what would the left and right hand end behavior of A up there look like? So it's 1/4 x cubed minus 2x. What would the end behavior be? You got up, up, down, down, and down, up. Down, then up. So because it's odd and it's positive, it's going to start low, end high. So it's down and then up. What about the next one? Yeah, it's negative odd, so it's going to start high and end low. Okay. One other thing about polynomials, you'll often have the zeros of the function will help you out a lot, because the zeros of a function are the same thing as the solutions. Graphically, there's the same thing as what? X-intercepts. Okay. So literally, if you say zeros, solutions, factors, x-intercepts, you're essentially talking about all the same thing. Factor being you need to do one step to get there yet, but it tells you those x-intercepts. Okay? So yes, you'll have to do some factoring. So if I want to find all the real zeros of this polynomial, what would I do? Factor it. So I'm going to factor it and set it equal to 0, so I'm just going to set it equal to 0 now. How can I factor this? Take out an x, and then what's left, the x cubed, or x squared, sorry, minus 12x plus 36. That'll factor into what? X minus 6 times x minus 6, which is x minus 6 squared. So that tells me what zeros do I have? What x-intercepts do I have? Yeah, this gives me x is equal to 0. This gives me x is equal to 6. Okay? Now, what's the end behavior going to be on this graph? Down, up. Go back to the original. Odd power. Positive out front is going to be down, up. Okay, so then if I think about graphically, well, it's got to hit at 0 and then hit at 6. So if I come up through, so start down, come up through 0, go through 6. Oh, wait a second. I can't go back up. Why? What's that called when there's two of them? Starts with M. What? Multiplicity. Yep, multiplicity. This has a multiplicity. Remember that word vaguely? We did it in FS&T, but I don't know if you talk about pre or plus or whatever they called it last year or not. So the idea, this has a multiplicity of 1 because there's only one x that refers to that 0. Because of the squared sign here, this is called a multiplicity of 2 because see that it happens twice. There's 2x minus 6's there. So graphically, it's going to pass through whenever there's an odd multiplicity, and it's going to rebound off whenever there's an even multiplicity. So I have the end behavior down up, and I have those 2 points. I can also tell that it bounces off the x-axis at the 6 value. Okay?
So even is bounces off.
Yep.
And odd is.
Because even basically causes almost think of it this way. Even causes a parabola-like behavior, so that's why it bounces off. Okay? And graphically, if I punch this into the calculator, it's going to look fairly close. It's not going to be exact. But if I do the x cubed minus 12x squared plus 36x, it should go through at 0 and then rebound at 6. Yeah, I didn't draw it quite steep enough, but for a rough sketch, it's good enough for now. Does that make sense? Okay. And multiplicity-wise, this is kind of the box that talks about repeated zeros or multiplicity. Whatever that power is, once you factor it, if that k value is odd, it's going to cross through the x-axis at that 0. If it's even, it doesn't cross. It rebounds off of the x-axis. Yeah?
What if there's a multiplicity of 3?
Well, then that would be odd, and it would go right through.
It just goes through and it
Yep.
doesn't-
Any odd, to the 3rd, to the 5th, to the
So, like-
to the 7th, so on and so
And
forth.
then you just don't see the other ones on the graph, like they're
Correct.
okay.
Okay? And those boxes are in the book if you want them. So if I want to sketch this, what can I tell about it? Just looking at the equation. It's going to be down up to start. Okay? It's got 3 zeros, most likely, but some of them might have multiplicities going on. Because what's the greatest common factor? 2x squared. That leaves me with what? X minus 3. So that gives me zeros when either of those is equal to 0. So I have x is equal to what? 0 and 3. Do either of those have multiplicity? 0. So if I go to graph this, it's going to start down, and then what's it going to do? Yeah, at 0, it's going to ricochet off, and then it's going to go down and back up through 3. So there's a rough sketch. Okay. What about this one? Let's make it a little uglier.
Actually down, down.
Yeah, I would take out greatest common factor for the fractions. First, though, what's the end behavior?
Down, down.
Down, down. Okay. So if I'm going to take out x's, I can take out x squared. I'm actually going to take out this entire coefficient just to get rid of it. I'm going to take the negative with it as well so that I can factor what's left. So what do I have for the first term after I take out negative 1/4 x squared? X squared. And then next will be minus what? Now stop and think about it for a second. When you're factoring it out, you're literally dividing by 1/4, right?
6.
So 6, because 3 halves divided by 1/4 is the same as taking 3 halves times 4. 3 halves times 4 gives you 6x. And then lastly, plus 9. Okay, those fractional ones take a little bit of practice to get used to, but the other thing you can do, you can also, if you have a hard time seeing that, make it so they all have the same denominator first. So rewrite this as 6/4. Then when you take out the 1/4, it makes it a lot easier to see. Then x squared minus 6x plus 9. X minus 3, quantity squared. Set that equal to 0. So I get x is equal to, and x is equal to 3. And both have multiplicities. So the end behavior was down, down for that. You have 0 and you have 3. So what's it going to look like, roughly? Like an upside down W? What letter do we usually call that? M?
Yes.
Okay. Questions on this stuff?
I didn't even think about that until you said it.
Somebody said it first hour too. Upside down W. Okay, so one more thing to talk about. And honestly, this is one of those kind of does statements in math. Something called intermediate value theorem. What this is talking about is that if you have two values up here, A and B on the X, okay? Somewhere, those then have a corresponding f of A and f of B, right? When you plug them in, they give you the y value. Well, this is saying that somewhere between here is a C value. That C value corresponds to some f of C value that's also between these two. So if I know boundaries for A and B, and I know their outputs here, somewhere in here there's a value where you get every single possible y value and every single possible x value. The reason I call that's a does statement, if I have 2 points here and it's a polynomial, I have to get from here to here somehow, right? No matter what, I'm going to hit every single value of x from here to here if it's a polynomial, because there can't be any gaps, right? I'm also going to hit every single y because there can't be any gaps. That's what this is talking about. Now, the reason they actually have this, it goes back to trying to generate an equation or a graph, trying to find zeros of really complex polynomials. When it's x to the 5th, when it's x to the 6th, things like that, when it doesn't factor nicely. Okay? Now, I'm not going to make you go through this full process because we can cheat a little bit, right?
Yeah.
What this is doing is allow you to find, if you find a value where A is positive and where B is negative, somewhere between there you have what? A 0. So the idea, this allows you to narrow down your zeros by repeatedly figuring out where they're at. So I'm not going to bother with this exactly, but the idea is, if I don't know where these zeros are, I can roughly figure them out, because this thing doesn't factor nicely here. But the idea is, if I plug in a 1, what am I going to get here? If I plug in a 1. So I have negative 1 plus 3 minus 2 plus 2. Negative 1 plus 3 is 2. So if I plug in a 1, I'm going to get a positive 2 out. Okay? So I want to pick some other number that if I plug it in, I'm going to get a negative number out. So if I plug in a 4, what's 4 to the 5th power without the calculators? 216? No.
No, 66 times 4.
Be 4 to the 5th would be the same as 2 to the 10th, right? 2 to the 10th? Bigger than that. 1024. So, but notice that's negative. Then 3 times 4 to the 3rd. What's 4 to the 3rd? 64 minus 8 plus 2. Is that going to be positive or negative? It's going to be negative. Some negative number here. So the idea is somewhere between 1 and 4 I have a 0.
Yeah.
Right? So then the idea is to narrow that down. Go between 1 and 3, see if there's a 0. Go between 1 and 2, see if there's zeros there. Then keep doing that repeatedly over and over and over again. Eventually, you can get down to the hundredths place as far as where that 0 is. I'm not going to make you do that by hand, okay? You can use the calculator for that. But imagine, before you had calculators, guess what? If you wanted to find zeros for complex things. Now, there is a cubic formula. So if you can break it down to something cubed and something that's squared, then you can actually do it with a quadratic and a cubic. There's programs that can do this. Your calculator can do this. You could write a program that could do this as well. Wolfram Alpha will do this for you. You can always write it yourself. Questions on any of this stuff? Okay.